So
What section is this?
this is 2.5. So this is the last section in chapter 2 of our book. So we're going to look at variations. And so variations are types of word problems that are used a lot. And so let me just kind of read through this little blurb in the book. So when mathematical models is developed for real world problems, it often involves relationship between two quantities that are expressed in the terms of proportionality. So like force is a proportional to acceleration. When an ideal gas is held at a constant temperature, pressure and volume are inversely proportional. We say that force of an attraction between two heavenly bodies is inversely proportional to the square of the distance between them. Revenue is directly proportional to sales. So those are just like some examples of statements that illustrate these variation problems. And so let's look at the different terminology that you might get. And this terminology is going to help you write out the equation. And so varies directly. So you might get something that says varies directly. And that's way too thick. Make it smaller. Okay, so varies. So if you see something that says let X and Y denote two quantities, then if Y varies directly with X, that's one way to write it. Or another way you might hear it is Y is directly proportional to X. Then you're going to write your equation the following way. So Y is equal to K all times X, where we say that K is called the constant. Of proportionality. Okay, I tend to like Y varies directly with X better, but sometimes it is Y is directly proportional to X. And so what's going to happen is they're going to give us some statement like this, and we would set up the generic equation that they give us. Once they do that, they're going to give us enough information about the problem where we can plug in information to figure out what K is. And then the next step of the word problem is that they're going to ask you to solve something. And once we know what K is and what the general form is with K, then we can solve anything they throw at us. So that's what's going to happen. But let me give you, there's a couple other ones that we need to know. And so if we're looking at varies inversely, so this is varies directly. So varies inversely. Or it might say inversely proportional. I'm not spelling that right. Proportional. That just disappeared. So again, X and Y are our two quantities. I'm not going to write that again, but if it says that Y varies inversely with X, so Y varies inversely with X, then we would write this as Y is equal to K all over X, where again, K is our constant. This is the main thing in these problems. The other way they would say it is Y is inversely proportional, or Y is inversely. And then the last one is Y can vary jointly with two values or more than two values. Where did they put it? They didn't write one down, but let me do it anyway. So Y varies jointly with, let's say, X and Z. And then how we would write this is Y is equal to our K, which is our constant. Jointly just means multiplication, X times Z. Or it would say varies jointly proportional. Okay, so knowing that, let's do a couple just setups, and then we'll go into the deeper word problems. So let's say you have the following. It says the cube of Z varies directly with the sum of the square of X and Y. Okay, so in these problems, we want to write a general formula that describes each variation. And then they give us a little bit more information about this. They tell us that Z is equal to 2 when X is equal to 9 and Y is equal to 4. So we're just going to go through first and we're going to nitpick this and write out the equations. And so the first thing that it tells us is the cube of Z. I think to myself, how can I write the cube of Z? Well, that is written as Z cubed. I don't know if I've expressed this to your class already, but my Z's, I have that little bar in between so that you know that's a Z and not a 2. So it can get confusing. So I have Z cubed. So this says now varies directly. So right there, when it says something like that, varies directly, varies proportionally, I know I need that equal sign. And I'm always going to have that constant K. And that constant is special to this problem. And then let's go through and figure out the rest of what they want us to write. Okay, so it varies directly with the sum of X and Y. Well, actually, I thought I missed something. With the sum of the squares. With the sum of the squares. of X and Y. Okay, so it varies directly with the sum. So I'm going to put a parentheses here. And it's telling me with the sum of the squares. So I'm going to square my X value. Plus the Y squared. Okay, so this right here, this is the general form. We just did the setup for the general form. So now what we need to do is we need to figure out what K is. So let's find K. And rewrite the general form. With the constant K. Okay, so if we go back and we go through and plug in values, they gave us what Z is. So it's telling me to take 2, and then it tells me to cube that. This is equal to K, which I'm trying to find, all times X squared. Well, X is 9, so 9 squared, plus Y squared, and Y is 4. So cubing 2, 2 times 2 is 4, times 2 is 8. So this gives me 8 is equal to K times, well, 9 squared is 81, plus 4 squared, which is 16. So 8 is equal to K times, well, 81 plus 16, that gives me 97. That looks like a 0 over there. That's fine. It's not erasing data. Are you guys getting a lag?
Just a little bit of it.
We're going to do that. That would look like a 0. I think that sometimes the program looks at shape, or thinks something's a shape and puts it in there for you. And so that parentheses, I think, looks like an ellipse, but it wouldn't erase. So get K by itself. We're going to divide both sides by 97. So K is equal to this 8 on the other side divided by 97. So we're going to take this general form, and we're going to leave the variables in there except for K. We're just going to plug in that 8 over 97. So our formula is Z cubed is equal to K, which is 8 over 97, all times X squared plus Y squared. Nope, it doesn't like that. Okay, so I pulled out one of the harder ones to start with. See, look at how nice that box is. Just made it after I did it, except that one didn't turn out very nice. It doesn't recognize that's a rectangle. Pleasures in life, the little things. Okay, let me just pull out a word problem now. I'm gonna put on the page so that you can refer if you ever wanna go back in the book, but in our textbook, you can go to page 195 to find the following word problem. So I'll read it, and this problem, let's do physics. So let's do problem number 26 in our textbook. I'll read through it, and then we'll nitpick it and pull out the important information, and then go from there. So it says the velocity v of a falling object is directly proportional to the time t of the fall. If after 2 seconds, the velocity of the object is 64 feet per second, what will the velocity be after 3 seconds? Okay, so again, a lot of information there, but we're gonna go through and just nitpick it. So it says the velocity v, so v is equal to the velocity of a falling object is directly proportional to time t. Well, v, it says, is directly proportional, so I know equals k times, so it's proportional to the time t it takes to fall. So we're going to let t equal the time the object is to falls. And so directly proportional was times t. Okay, so there is our generic equation. Now they're going to start throwing out information at us so that we're able to figure out what k is. So they say if after 2 seconds of the velocity of the object is 64 feet per second. Okay, so they say when t is equal to 2 seconds, then v, our velocity, is equal to 64 feet per second. So then they want to, they're asking us a question to find something. But before we even do that, we want to go in and we want to plug in those values so we can figure out what k is. And then, like I said, we can answer anything that they throw at us about this problem. So go in and plug in what v is. In our case is 64. This is equal to k, which we're trying to solve for. And the time when it was 64 feet per second was 2 seconds, so times 2. So if we divide both sides by 2, we can get k by itself. So k is equal to 64 over 2, but that reduces. So k is equal to 32. So we now have our equation. So v is equal to k, which will always be 32 in this case, times t. So the question now is, what will the velocity be after 3 seconds? So what is the velocity? Well, I know that's giving me time. So I know my t is equal to 3. And I just plug that into the equation we just found. So I know my velocity is going to equal 32. My velocity is equal to 96 feet per second. Sometimes to me, again, they like, oh, wow, this is a lot of information that they're throwing at me. But if I read it and then go through and just take it in little chunks, it's not too bad. Okay, so the cost C of roasted almonds varies directly with the number A pounds of almonds purchased. If the cost is $23.75 when the number of pounds of roasted almonds purchased is 5, find the linear equation that relates the cost C of the number A of pounds of almonds purchased. Then find the cost C when the number of pounds of almonds purchased is 3.5. Okay, so the cost C of roasted almonds, so C equals the cost of almonds. Varies directly. Okay, so right here it's starting to give me my equation. So C is equal to, varies directly, so I'm always having this K in here. With the number A of pounds of almonds purchased. So A, different color. A is equal to number of pounds of almonds. That makes sense, right? That's it. And then it starts telling us some information. So it tells us the cost is 23. So C is equal to 23.75 when the number of pounds of roasted almonds is 8. A equals, I don't know if I said 8, but it is 5. It's 5. So plug it in to figure out what K is. We have 23.75 equals K all times A, which is 5. We can get K by itself by dividing both sides by 5. So we have 23.75 all over 5. Which is 4.75. So K is equal to 4.75. Basically, this is telling me that it's $4.75 per pound is what the cost of almonds is. So C is equal to 4.75 times A, which is the number of pounds of almonds purchased. Last part of the question says, and find the cost C when the number of pounds of almonds is 3.5. What is the cost when 3.5 pounds? So C is equal to 4.75 times the number of pounds, which was 3.5. So 4.75 times 3.5 gives us, and I'm going to round to the nearest cent. So it's $16. And so 625. So the 5 is going to round up that 2 to a 3. So it's going to be 63 cents. Okay, so the cost is $16.63 for 3.5 pounds of almonds. And let me just tell you what problem that was, just in case. So this was number 30 in the book. Same page.
What page was that?
The page is 195, number 30.
Thank you.
And then just flipping one more page. So I'm on page 196. And let's do 46. Okay, so we're talking about building and safe load for a beam. So the maximum safe load for a horizontal rectangular beam varies directly with the width of the beam and the square of the thickness of the beam and inversely with the length. Okay, maybe we should just take that piece. So the maximum safe load, maybe they give me some variables to go. Okay, so maximum safe load of a beam. I don't know what variable you want to let that be. Maybe let that be equal to n for max. Maximum safe load of a horizontal rectangular beam varies directly. So right now I know I have my equal sign in there. And let me go down here so we can put in the variables up here. So m is equal to, so I need my k value. So it varies directly with the width of the beam. So width of the beam. Or maybe that be w. It varies directly with the width of the beam and the square of the thickness of the beam. So maybe T could be the thickness of the beam. That is the thickness T. So it said the square of the thickness. So we have to put in the square in here, T squared. And inversely with a length. So inversely with a length. That means I'm going to go over. This is going to go on the bottom L. So the length is equal to L. Let's just go through, just read that one more time, make sure we set it up right. So the maximum safe load of a beam varies directly equals K with the width of the beam and the square of the thickness of the beam and inversely with a length. Okay, so given the following information, we're given that if an 8-foot beam will support 750 pounds, so we have a 8-foot beam, so I know what the length is. Is 8 feet. It will support, so that's going to be my maximum load, up to 750 pounds. So max load, £750. Right now we have L is 8, M is 750. When the beam is 4 inches wide, inches. So W equals 4. And 2 inches thick. I did the wrong color for one of those. Oh well. The thickness.
I'm assuming this is a metal beam because a 2x4 cannot hold 750 pounds at 8 feet. I know from experience.
Okay. um, okay, so maximum load. This is should be blue. 750. So plugging it into our equation, we can use this to figure out what K is, and then we can answer what they ask us. So we got 750 is equal to K, which is we're trying to find, all times the width, which we're given is 4, all times the time, or not the time, the thickness, 2, which it tells us to square it, inversely, so all over the length, which we're given 8. So let's kind of simplify this. So we have 750 equal to, well, I know this 4 goes into 8, so I can actually start canceling a couple of things. 4 goes into 8 twice, which means that would a 2 squared over 2, that's 2 would cancel with one of those two. So really what I'm left with on this side by simplifying is 2K is equal to 2K. So I can get K by itself by dividing both sides by 2. So I get 750 divided by 2 is, what is that? 2 goes into 7 3 times, the remainder 1. 2 goes in there 7 times, the remainder 1. 375. Okay, so K is 375. So we're going to go in now, plug it back into this equation, and we can find what we need. So we have the maximum load is equal to 375, all times our width, all times the thickness squared, all over the length. This is the equation we now want to use. Didn't like my rectangle that time. So now what are they asking? What is the maximum safe load in a similar beam, 10 feet long, 6 inches wide, and 2 inches thick? Okay. So what is maximum load? And the similar beam, make sure that's, that's similar. Just like Noah was saying, it depends on the material. So don't go out here and try this. I don't know if this is going to work for the material you're trying to use to build and stand on. Okay, so what is the maximum load, safe load in a similar when the beam is 10 inches long? So that's our length. Not 10 inches, 10 feet. 6 inches wide. And 2 inches thick. Just go in here, plug it in, and then we have our answer. So the maximum load is 375, all times our width, which is 6, all times the thickness, which is 2 squared, all over the length, which is 10. Just wanted to kind of simplify first. So I know that 5 goes into both 375 and 10. 5 goes into 10 twice. 5 goes into 375. Well, 5 goes into 37 7 times. With the 2 left over, so it's 75 times. Let me just reduce a little more. 2 down here in the denominator could cancel out with one of these 2's up here. So we really just left with 75 times 2 times 6. How about let's do it this way. 2 times 75, because we can reverse order when we multiply, is 150. 150 times 6. So I can multiply. 6 times 0 is 0. 6 times 5 is 30. So I'm going to put my 0, carry my 3. And 6 times 1 is 6, plus 3 is 9. And so we were in terms of pounds. So maximum safe load for that type of material, that you had a length of a 10-foot beam, 6 inches wide, 2 inches thick, could hold 900 pounds. You want, I don't know if I can. Okay, so we just looked at and finished chapter 2. So let's stop the video. I want to stop.